Okay, so we are in section 7.4, exponential growth and decay. This is our last lesson for all of AB calculus. So after this lesson, we will be ready for the test on differential equations, and then we can start the review. If you guys remember from last time, the exponential growth and decay models were given by this differential equation, which we see right here, that dy over dt equals k times y, where y could have been, bacteria or population or something like that. Y is your function, which is what we are taking, which is what we have the differential equation of. It's our rate of change, how y is changing over some time. K is your constant of proportionality. This is a direct variation constant. And the idea was, if y was differentiable over time, and y is a function which is greater than 0, you get this y prime equals ky. The y prime, of course, is the same thing as dy dx equals ky. I'm sorry, not dx, dt. How y changes over time. And the constant, again, in proportionality was k. If we did that, you should have noticed every single time we did this, and you went through the entire process of separable differential equations, you ended up with this guy right here, y equals ce to the kt. So if it says that what we have is a normal growth rate, which is what we have here, if it says we have a normal growth rate, it's always going to give us this y equals ce to the kt. C is always going to be the initial value, so it's your starting point, whatever the initial, again, population, bacteria, whatever it is we're starting with, amount of money, stuff like that. That's always going to be the starting rate, and K is going to be your constant of proportionality, T is your time. If we have exponential growth is going to be when your K value is greater than 0. And that should make sense if you think about it. You're taking an exponential e and you are raising it to a power which is positive. Therefore, it should be a growth. Likewise, if you're going to have decay, you're going to have e to some negative power, and that would be a decay model. K would have to be less than 0. All right, let's take a look at some examples. First example, a village had a population of 1,000 in 1980 and 1,200 in 1990. Assuming that the population is experiencing natural growth, there's that word, natural growth, what will be the population in 2010? So we could start off with a differential equation here, but since it says natural growth, we can go straight to that equation. Because it says natural growth, we can go straight to that equation. We don't have to worry about solving the differential equation. What we do, however, have to do is get C and K. So what the information gives is that it had a population of 1,000 in 1980 and 1,200 in 1990. So that tells me that the current population, the current p-value is 1,200. The original p-value, the place we started off at, was 1,000. Don't know k yet, so we got to put that up there. And the time elapsed, in this case, looks like it was 10 years. You're going to have to use 1980 as your initial time and 1990 as your second time. So that's 10. That gives us what we need now to solve for k. divide both sides by 1,000, you're going to get, what is that, 1,200 over 1,000, which is the same as 12 over 10, and that reduces to 6/5. That is e to the 10k. In order to get the k out of the exponent, we're going to need to take the natural log on both sides of the equation. So we'll get the natural log of 6/5 equals the natural log of e to the 10k. Purpose for doing that is because the natural log and the exponentials, again, are inverses. So if you use your property, you can bring the 10k out to the front of the natural log. And of course, the natural log of e is 1. So the entire right side simplifies to 10k. The left side is just the natural log of 6/5. Nothing else we can do there. Then to solve for k, we're going to divide both sides by 10. But I will write that as 1/10 the natural log of 6/5. Same thing as dividing by 10. And that's k. Again, at this point, don't plug this into your calculator and round anything. If you do plug this into your calculator and want to write the decimal, you need to write as many decimal points as you can possibly do. Either way, it's going to be tedious to write out k that way, but it's better just to leave it in this form for now. Okay, so the population equation now that we get. Population is going to equal the initial, which is 1,000, e raised to the 1/10 natural log of 6/5 all times t. And the actual question is asking us, what will be the population in 2010? Well, we have to figure out, first of all, what the time is that we're going to put in, considering that we started at 1980. The difference between 1980 and 2010 is 30 years, so 30 is going to be our t value. So our population in 2010 is going to be 1,000 e to the 1/10 natural log of 6/5 times 30. From here, this is where you plug this into your calculator, and ironically, this one actually works out to be an exact whole number. The population in 2010, after you plug this in, works out to be 1,728, and we are talking about people. So we'll include the units. All right, let's see how we're doing on time here. Okay, we're just a little over 8 minutes. We're doing okay. Let's go on to the next problem. Radioactive decay. Radioactive decay is measured in terms of what's called half-life. If you've taken physics before, maybe even chemistry, you probably know something about half-life. Half-life is basically how long it takes, or how much stuff is left, whatever it is that you're trying to have, how much stuff is left when this thing gets to half of its life. So, in other words, in our case, suppose we have 10 grams of plutonium, which is released by the Chernobyl accident, which is back in the 80s. You guys weren't even born yet, so you may not know about that stuff yet, unless you've taken some world history. How long is it going to take for the 10 grams to decay to 1 gram if the half-life of plutonium is 24,360 years? That's a long time. Plutonium lasts forever. So what that says is 24,360 years from now, however much plutonium I start with, it's going to be half of that amount. Okay, so we're going to let y be the mass in grams of the plutonium. Because the rate of decay is proportional to y, we know that we're going to get that y equals c e to the kt. So y equals the initial amount, which was 10 grams, e to the kt. Okay, so we're going to need to be able to try and figure out here k. The problem is what they don't give us, or what they do give us, is they give us that We want this thing to decay to 1 gram, but we got to find K first because we don't know how long it's going to take to get to that 1 gram. What we do know is that it's going to take 24,360 years to get to half of 10. Of course, half of 10 is 5. And it's going to take K times 24,360 years. And that's going to allow us to find K. So we'll divide both sides by 10. What a coincidence. It gives us 1/2. Makes sense. We're talking about half-life. One half equals e to the 24,360 k. To solve that, we're going to have to take the natural log on both sides. Of course, the natural log of the right side over here is going to give us just 24,360 k. And then to solve that for our constant of proportionality, we're going to divide both sides by the 24,360. Again, I'm going to write it as 1 over 24,360. Natural log of 1/2 is our K value. So that makes Y 10e to the 1 over 24,360 natural log of 1/2 t. Okay. So now here's where we kind of have to be careful because we want to know how long, that's what it's asking is how long. So we're solving for t. How long it's going to take for the 10 grams to decay to 1 gram. So the 1 becomes our new amount. And if you notice, it's going from 10 to 1, so it should be a decay. If you were to actually plug the natural log of 1/2 into your calculator, you would see that that is a negative value. So your K actually is negative, and it is a decay model. A little tedious to keep writing all this stuff out, but better safe than sorry. Okay, so again, the idea is to solve this for t, we're going to have to get the exponential function on the right-hand side isolated and then take a natural log on both sides. So we got to divide by 10 on both sides. And we get 1/10 on the left. Again, that should really make sense if you think about it. You're going from 10 down to 1 gram. It is 1/10 of the original. And then to get the t out of the exponent, we're going to have to take the natural log on both sides. Natural log of the right side, the e in the natural log will go away, and it leaves us with that. To solve for t, multiply both sides by 24,360. And then divide both sides by that natural log of 1/2. And that's going to be how long it takes to get down to 1 gram. Now, considering that it took 24,360 years to get down to 5 grams, it's going to take a really long time for this thing to get down to 1 gram. So if you plug all that into your calculator, what you end up with is 80,922 years. That's a long time for this plutonium to stick around. This is why they had to quarantine off Chernobyl for such a long time. Too much plutonium left around. Okay, moving on. Okay, this one is similar to the ones that we've done before. A little bit of a difference here. It's all in the wording, so you have to be really careful what you're reading. It says 1 hour after a bacteria culture was started, there were 300 organisms. And 2 hours from the start, there were 900. So we're actually starting past the time 0. So we're going to have to basically rename our time 0. And then how many organisms will be left, will there be 4 hours after the start? So again, everything has to be based upon your starting time. That's the key. It is a standard growth. So the initial amount that we're going to use is 300 because that's the first value that we actually know. Okay, the new value that we're going to use, because it says that we've got 900, 2 hours from the start. So 900 is our new population. But the big question is, what goes in for T? Well, the 300 was 1 hour after we started. The 900 is 2 hours after we started. So really the 900 is only 1 hour from the time that it was 300. So T is 1. It took 1 hour to get from 300 to 900. That's the difference in your times. That's what you have to plug in there. So dividing both sides now by 300 gives us that 3 equals e to the k. This one will be much easier to deal with because now when we natural log both sides, you get the natural log of 3. Natural log of e to the k is k. So we get our k value to be the natural log of 3. So our population equation now becomes 300 e to the ln of 3 times t. And it says how many organisms will be there 4 hours after the start. Well, there's going to be, let's see, first of all, the time. 4 hours after the start is really how long after there was 300. Well, that would be 3 hours after we had the 300 amount. So the population of this thing is going to be 300 e to the ln of 3 times 3. And then plugging that into your calculator, again, this one just happens to work out to be a nice whole number. Doesn't usually work this way. It's 8,100. 8,100 bacteria in only 3 hours after our first test at 300 and 4 hours after the initial time of the test. Okay, we're going to do one more half-life type problem. Number 4, we've got a sample of an isotope initially weighing 90 milligrams. After 100 days, 60 milligrams remain. Again, key in the wording there is that it's telling us how much we started with and how much is left. After how many days will the sample be down to 20 milligrams in mass? Again, standard exponential. The initial amount that we're given is 90, so there's our C, e to the kt. Okay, we're going to have to do what we can to find k first, because we have to have that other variable. So we're given that 60 milligrams is left, so that's our new amount. So it's going to be a decay. We went from 90 to 60. E to the k times our time here, which is going to be, what, 100 days? Okay, same exact process. We're going to divide both sides by 90, so we're going to get 60 over 90, which is 2/3, e to the 100k, natural log on both sides. And then dividing by 100 is like writing 1 over 100 out in front. There's our k. So our population equation here is 90 e to the 1 over 100 ln of 2/3 times t. After how many days will the sample be down to 20? So now we're looking at 20 being our new one. Okay, what's different about this kind of a problem is when it gives you a percentage, then sometimes you have to realize, well, what's the percent going to be if I'm have a certain percent left or what I'm down to. You just got to be really careful on the wording on that one. This one's pretty much the same as what we've done. So dividing 90 on both sides, we'll get 2/9 e to the 100 natural log of 2/3 t on the right-hand side. Again, natural log will just give us 1 over 100 natural log of 2/3 t. So we'll have to solve for t by multiplying both sides by 100 and then dividing by the natural log of 2/3. That is an exact time. Of course, again, tell somebody that that's how long it takes and they're not going to have any idea what you're talking about. So we will go ahead and do our approximate decimal here. This one actually does work out to be a decimal. So you remember you have to go 3 decimal places. And when you plug that in, you get 370.951 days. So whatever this thing is, this isotope, definitely doesn't have quite as long of a half-life as the other one did. This one takes 370 days, about 371 days, to get from 90 milligrams down to 20, so that's not nearly as bad. All right, one more example, and this is probably the key. This is probably the big one. So, got this thing called Newton's law of cooling. What it states, I'll just read this, it states the rate of cooling of an object is proportional to the temperature differences between the object and the surroundings. This is just a really fancy way of saying, if you look at this equation, this is the same as dy dt equals ky, where y is just the difference in the temperatures. Now I always put this where the temperature of the object is the T sub O. I know they don't have the O on here, but I like to put the little O there because it just tells me that's the temperature of the object, and then the temperature of the surroundings is whatever you're placing the object into. So again, think of putting a turkey into an oven. Well, obviously that's not cooling, that's heating, but it's the same basic idea. Think of taking, in this case, a soda can and putting it into a refrigerator. You know, it's going to cool itself down. So you've got a temperature of the object that you place it in, then you're going to take the temperature of the surroundings and subtract them. That's really the only difference. So we have to just think of that T sub 0 minus T sub S as being Y. It really is the same exact thing. So if we start off with how the temperature is changing over time, a little confusing there with the T's. Capital T I'm going to use for temperature, lowercase t is for time. It's just K, oops, I'm going to write this as Y of T, where again, Y is just a function of time. I'm sorry, not time, temperature. Y is a function of temperature. Because Y is just the difference in your temperatures, the difference in the object minus the difference in the surroundings. So if you separate these, which is what we're going to have to do, you're going to get 1 over Y of temperature equals K. Keep forgetting the dt equals K little dt. Okay? Then, you know, it's the same process. You're going to go through the whole integration process, and the 1 over Y is going to give you the natural log. The right side is going to give you a kt plus c. You'll exponentiate both sides. We've done this several times. This is just going to give us y equals c e to the kt. The biggest thing is to remember that y and c, let's write this over here, y and c are both functions of temperature, which means you're going to have to use Newton's law of cooling on both of them. So the initial temperature, that's your C. Let's go back up here to this thing. the initial temperature. The bottle of soda was put in at room temperature. So this was the initial temperature. That's the temperature of the object. That's the initial temperature of the object. It's placed into a refrigerator where the temperature is 44 degrees. So this is the temperature of the surroundings. So that's the initial. That's your C. So C is going to be, let's go back up here and see what the value is, 72 minus 44. Okay, using Newton's law of cooling, that's the initial temperature. So what is that? 72 minus 44 is 28. And we're also going to need to know what y is because we got to plug both of those things into our equation. Well, the new one, that's the current one. It says after a half an hour, the soda has cooled to 61 degrees. So we're going to have to do 61 from right here minus the 44 because it still is, this is the temperature of the object now, minus the surroundings, which is still 44. The refrigerator hasn't changed temperature. So 61 minus 44 is our y value. And 61 minus 44 is 17. So that's what we're going to plug. Take all this and plug that stuff into here. So we're going to ultimately end up with, let's move this back up a little bit, y equals C, which was 28. Actually, we don't need the y anymore because we have that. Y is now 17. That is our current temperature. Equals 28 e to the kT. Okay. Now we have enough information to solve for K because it does tell us how long it takes for the temperature to get from 28 cooled down to 17. It takes, according to this, 30 minutes. So you can either put that in terms of minutes or you can put it in terms of hours, but stay consistent. If you use 30 minutes, make sure you use minutes throughout. If you use hours, make sure you put that as 0.5, and everything else has to be in terms of hours. So we get 17, I'm going to stick with minutes, 28 e to the 30 k. Okay, and then again, solving for k, we keep doing the same thing over and over again. 17 over 28 equals e to the 30k. Natural log both sides. Gives us 30k on the right, and then dividing by 30 is the same as 1/30th. The natural log 17 over 28 equals k. All right, so that's our k value. We can plug that back in, and we're going to get y equals 28 e to the 1 over 30 natural log of 17 over 28 t. So that should allow us to find the temperature at any time t now. So if we go back up here, we are looking for, we are looking for the temperature after another 30 minutes. I actually gave you guys the wrong temperature, the wrong time at first. Got lucky because it was after half an hour. Now we want it after another 30 minutes. So in this case, it's going to be 60. Again, if you're using hours, that would just be 1. But since I'm using minutes, I'm going to plug in 60. So the temperature at 60 minutes is going to be 28 e to the 1 over 30 natural log of 17 over 28 times 60. Okay, and then you go and plug that into your calculator, and we get that y of 60 is approximately equal to 10.321. And you might say, wait a minute, Mr. McCoy, that doesn't make any sense because The temperature of the refrigerator was 44 degrees. How is it that my soda is now down to 10.321? That doesn't make any sense. You're right, it doesn't make sense, but you have to remember that Y is the temperature of the object minus the temperature of the surroundings. So in this case, we have to add back in the temperature of the surroundings, and the temperature of the surroundings was 44 degrees. So the actual temperature after 60 degrees, after 60 minutes is approximately 54.321 degrees. And that's what we're looking at. That makes a lot more sense. So it took about an hour to get this can that started off at 72 degrees to cool down to 54.321 degrees. And as a matter of fact, what you should notice is that anytime you do a cooling where you take an object from a surrounding and put it into another surrounding, it can never exceed or go below the surrounding temperature. And there is a second part to this question, and then we'll be done, is how long does it take for the soda to cool to 50 degrees? So now we're actually going to solve for time, same general idea. Let's extend that a little bit. So this time we're going to go back to the original equation, which was y equals, I think it was 28 e, let's check that out, 1 over 30, natural log of 17 over 28, times t. We are now solving for t. The question is, how long does it take for the can, keeps doing that, how long does it take for the can to get to 50 degrees? Well, if it took it 60 minutes to get to 54.321 degrees, should take a little more than an hour to get there, at least you would think so. The biggest thing is you got to remember again that Y is the difference in the temperature and the difference of the surroundings. So we want to figure out how long it's going to take to get to 50 degrees, and the surroundings again were 44 degrees. So Y is 50 minus 44, which is 6. All right, real quickly solving this thing for t. We're going to get 6 over 28. 6 over 28 reduces to, what is that, 3/14? Not exponentiating natural log both sides. And then solving for t, we'll multiply both sides by 30 and then divide by the natural log of 17 over 28. So we get 30 natural log of 3/14 over the natural log of 17 over 28. Again, just be real careful when you plug that in your calculator. And this works out to be a time of approximately 92.613 minutes, or just a little over an hour and a half. So it took a little over an hour and a half to cool a room temperature can of 72 degrees to approximately 50 degrees, given the fact that we put it into a 44-degree refrigerator. All right, you guys have your homework, which is listed on the front of the packet. It's only 5 problems. You guys should be able to get it done, hopefully not too much problems. All right.